Day 1, week 22, learning a little bit more about thermal energy. This is our second week of our unit. We don't need to worry about the entry task, but throwing back to the Nearpod, when I was gone on Thursday and Friday, week 21, day 1, we had this idea that was presented in one of our videos that everything in the universe is made up of matter, that is made up of molecules, and these molecules will jiggle or they will move back and forth. And in that particular video from PBS, we saw that the molecules inside your body are very close together, and they're pretty warm because our bodies are warm. And when we think about a cold winter day, that the air outside is pretty far spaced apart, and that they're moving slower. They're colder than we are. This is a pretty advanced idea. It's something that we're going to spend a little bit more time on today with this food coloring lab. If you have supplies for that, if you've seen the email about what's going on this week, that is something you are, of course, able to follow along with, and if not, it is absolutely not something you are required to do. We're predominantly leading this as a lab, as an investigation, through demonstration. So, when we are talking about particles and molecules, what are these? Molecules? Matter? What is this stuff? It's what everything is made of. Your glasses, your shirt, the air outside, the sun, the clouds, the plants, all of these things are made of matter, and at that microscopic level, these tiny bits of matter are still there, and they interact together, just like a... Really? Well, no, we'll hold off on that idea. We'll come back to that analogy later. But at this microscopic level, these particles, or these tiny bits of things, are still there, and we might call them matter, or molecules, or particles, but really we're referring to that same thing over and over again, which is microscopic stuff that is responsible for helping us to warm up and cool down if we're talking about being outside in a winter breeze, if we're talking about wearing a jacket in the winter to try and keep that heat inside our body. All this has to do with the particles and how much energy they have. Bill Nye talked to you about the idea of heat versus heat energy. So how hot something is. We have an ice sculpture and we have a match. Which of them is hotter? The match, of course. If we were to take a temperature of these, that ice sculpture is going to be down below freezing, whereas that match is going to be hundreds of degrees. The match is hotter, but when we think about which one has more energy, Bill explained to us that actually that swan does. Even though it's cold, those particles are still moving. They still have energy. And since it's so much bigger, overall, that swan is going to have more total energy. And he explains this in the light of, this match, yes, it's going to be hot, but could it melt the entire swan? It might melt a little bit off the beak, might make it a little bit smaller, but overall that swan has more energy overall, and that again has to do with the particles of that swan, the molecules inside of it, and how fast they're moving. Since there are so many, even though they're moving slowly, that energy is still going to be greater than that of this match overall. So for this reason, we have this food coloring lab, this set of questions in which we are trying to make sense, a little bit frozen up. We're trying to make sense of these 3 different containers. And again, if you have this at home, that's great. Feel free to do it on your own. But what we are going to do is we are going to place some cold water in here. I have it in the freezer currently, just for a few minutes to get it a little bit more chilled. Some hot water, which was boiling, but I'll probably mix to bring it down so it's not too hot for me to handle. And some room temperature water that's just been sitting out. And I'll go through and I'll place a drop of food coloring in each of these, and we'll be able to visually see how this water is moving, how the temperature of these different waters is causing its particles to move. So why don't I go ahead and grab those supplies while you get started on your prediction. That prediction is, how is the food dye going to act differently in each of these? And again, we're just looking at something like this, some liquid food coloring that you might find in the baking section. You do not need to go out and buy this. This is something that the demonstration is enough, but if you have this at home, you're welcome to do it. If your family says, yes, we don't mind you working with hot water, just caution that hot water can burn if you're not being careful. Prediction, how is this food dye going to act differently in these 3 containers? Get some thoughts down. Feel free to pause the video if you need to, and I will bring the supplies over and get us set up. So what do we need to do? Again, this is that good opportunity to pause if you're not done writing down your predictions yet. But assuming you are done, you should have your cups. I am going to have my cups. I have one that's cold, one that I'm going to fill with a lot of falling things, one with some room temperature water. I'm trying to get them to the same level. I'll double check that in just a second. And my water is still very hot, so in my tea kettle, I'm going to pour a little bit of this room temperature water first so it doesn't melt my cup. And just kind of a quick feel test. Quick stir to get them mixed together. That'll work just fine. Okay. So, what have you predicted? Is the hot water going to act any differently than the cold water? Is the cold water going to act any differently than the hot? It doesn't really matter what you're predicting, because of course our observations are going to be the most important part. As far as those observations go, noticing that this one's just a little bit higher than the others, so I'll take just a touch of that water out, get it to the right height. Of course, in science, sometimes it's very important to be very precise. If we were doing this in class, we would measure out the same amount of water. For demonstration purposes, I'm just going to do it like this, and you can do the same at home. You can just kind of visually line it up. What are we predicting? Some students were predicting that it's going to spread out faster in the hot water. Some were thinking that it was going to act almost like boiling water. When you boil water, stuff's kind of moving and violently all over the place, that this might happen in the hot water. We'll take a look and see. And while that is happening, you should either have this open, if you can watch both of them side by side, or it's okay to wait. It's okay to observe this, write things down by hand, or draw them, or just observe them, and then write down, and you can rewind the video if you need to. But of course, we want to see everything that's happening. It should only take 2 minutes to really get the main activity, and we might watch it for a total of a little bit longer than that to see overall. But what do you observe? What do we notice? Most classes so far have decided to take the temperature, though that is not required. But we can do that here. 123.8 degrees Fahrenheit for the hot water. Just above 70 degrees, 70.2 for the room temperature water. And that freezer water isn't quite as cold as I'd hoped it would be. It didn't spend as much in there as your older classmates. Those were about 37, but this one's at 46 degrees about. That's an observation if you want it to be. 128. 70 and 45, I think it was. Nope, 122.9, 70.2, 46.0. I'm not going to write down the precise one, but you have the video accessible. You can back it up and get the precise temperatures if you want to. Let's go ahead and see what happens. And I'm going to be as precise and uniform with these as I can. Just a gentle little drop in. There goes 1, 2, and 3. All right. Now, obviously, the cold has a little bit of a head start, but it seems they're doing what? Watch, observe, enjoy. Oops. Now, this was a mistake on my part. I'm trying not to jostle these waters, but in moving my white backdrop, I did wind up hitting it and causing that cold water to shake a little bit more. Even so, it seems like this hot water fell straight down. It's kind of rising back up to the top now, and that cold is overall pretty unaffected. Feel free to pause at any point, go type down some observations, or just watch and type them up later. You see this almost swirling around. Is it possible that some of that was from my own stirring? Yes, but actually overall it did settle quite well. You also see that it's swirling upwards. It's lifting up from the bottom, and oh golly, gotta be careful, don't I? It's rising up from the bottom, and what we see is actually the exact same in the other two classes that I've had so far, which have not been disturbed by my bumping. We see that it is spreading out faster in the hot water than in the cold. The room temperature is somewhere in between them. The temperature's not too far off, is it? This one was 45 degrees, this one was 70, whereas this one is 122, so quite a bit higher temperature overall than the other ones. It seems over in the cold water, there's almost these little smoke plumes, these little rings that are dropping down, almost more like jellyfish actually, as they descend. For whatever reason, in the room temperature water, it seems to have gone mostly all to one side. But here, what evidence do we have? Well, after only a minute or two, it seems like every part of this cup has some dye in it. It's a little bit more concentrated down towards the bottom, but still, there's a little bit of dye everywhere. Here, maybe about half of the glass has dye in it, and the left side really doesn't have much. There are a couple of strands. Gosh, over here, it seems like less than a quarter of it has actual dye in it. Very concentrated on the bottom. It seems to have run down, and you need to be a little bit more careful about shaking the table, because of course that's going to disturb it too. But there's a ton of clear liquid on both sides that just hasn't even been affected by this yet. This is a great opportunity to write some of those thoughts down, and they don't need to be precise. They do need to be, by precise I mean they don't need to be a picture representation of this, though you're welcome to draw them. But you should describe with your words as accurately as possible what we see in these different situations here. What do we notice? We don't just want to say that red is spreading faster. I don't know why I called it red. I should say hot water. Hot water is spreading faster. How do we know this? What do we actually know? Well, the food coloring in the hot water spread across the whole container, while the cold was only, I'm just going to guess on this a little bit, less than 25% filled with dye. Again, what we're talking about there, even though there's some concentration down at the bottom, we can see everything. There's no clear liquid. It's all somewhat blue, whereas here there's still a lot that has not been impacted by that. We can describe the plumes, jellyfish-like. Some jellyfish plumes of dye falling down in the cold water. I'm just going to leave this running for another minute or so, and then we can check it again after final talk through. From a top and side view, it does seem like there is some concentrated dye. Kind of down at the bottom of each of the glasses. You can see some things behind them on the counter, a yellow rag for sanitizing and all that. That's irrelevant, of course. On the top, From the top, similarly, we can see this hot water on the bottom, which has a darker color overall and maybe just a tiny patch of concentrated dye that's left. Whereas this has a huge big dollop of dye there, and this has quite a lot around the rim as well, even though overall it's looking darker from the top. I think that's more about refraction than it is actual dye distribution in that cold water. So what are we going to do with this information? I hope you have more observations than what I've written down here. What else do we have? From that top view, hot has small spot of concentrated dye. The rest is spread out. Cold has a lot. There we go. Cold has a lot of concentrated dye around bottom rim. Room temp has a lot of dye concentrated on the inside. Though it's a little bit less than that cold water is. Where are we now? 5 minutes? 5 minutes. Red seems entirely spread out with limited concentration. Cold still has a lot of clear water that hasn't had dye mix in yet. Of course, this is going to continue on, right? So why is this happening? When we talk about these molecules, when we talk about these particles, at a microscopic level, this hot water, it has more energy. These particles are moving faster. What happens when these fast-moving particles interact with the food coloring? What happens over here when these slower-moving particles interact with the food coloring? Or in the middle, when these moderately speedy, kind of slow, kind of fast, room temperature water particles interact with the food coloring. All of them are going to interact with them a little bit differently based on that temperature and that speed. So your job is to do what we call a claim, evidence, and reasoning, a CER, where your claim is your answer. Do water temperatures affect the way food dye spreads? At a simple level, yes. Hopefully you'll expand a little bit with explaining just what you observed. What evidence do I have? Well, I know that the food dye in hot water spread out faster because I observed that after 3 minutes it had filled the entire container with blue, whereas with the cold it took up to 9 minutes. This is evidence. You're providing data. Maybe it's numbers, maybe it's just general observations. Reasoning is how you connect them. That evidence is the data. The reasoning is how are these things connected. So you might say, well, the fact that the cold one had water, it took 9 minutes before the water fully was filled with the blue, supports that it spreads slower. I need to restart the sentence. The fact that that hot water had blue dye everywhere in only a minute supports that it was spreading very quickly, compared to the cold dye, which took up to 9 minutes for it to happen. This shows that the water is moving the dye around faster because you'll have to forgive me at the end of the day. My brain is too mushy right now. I can't even remember what I said to my students in class, but I'm not going to re-record this because that would be a bad mistake of my own time. if you have thoughts or questions, I'm going to let you come to me on this one. Come to our office hours. We can touch base on this, and my brain will be at a little bit better place than it is at this very second in time. I'm going to let you give your own thinking, your claim being that answer, your evidence providing the data that you have collected, and your reasoning showing how your evidence supports your claim. Sorry I wasn't able to explain that better at this moment in time, but you're going to rock it, and you're also welcome to come out and we can work on it together, okay? Final look here. Even now, a while after we've started up, that blue cold water is still not fully there. Put a link to some other videos that show a little bit of a time lapse of this happening faster and slower for you to see it in a little bit greater relief, okay? You can check that out in the description below. Thank you so much for your time. As always, I'm here if you need me, have questions. We'll see you next time.